Hey, this is Kyle, and I'm going to be talking about part 2 of our homework. So part 2, we want to calculate the Frenice tangent and normal vectors for our helical curve. So a little bit about the Frenice formula. So you're describing a particle moving along like this helical curve, like the one we have. And it's composed of three vectors. So we have the tangent vector, tangent to the curve, the normal vector, and then we have the binormal vector, which is a cross product of the tangent and the normal vector. These three vectors are defined with respect to the arc length of the curve. And since our curve is not defined by arc length, we just have an equation for our curve. We want to look at another definition for these vectors. So the tangent vector t, first if we have a curve that's defined by an equation rt where t is not the arc length, which is what we have, then the tangent vector t can be defined as the derivative of our equation for the helix divided by its magnitude. This derivative here is going to be a vector, and then we divide by the magnitude of that vector. And like I said, that gets our tangent vector t. And then we have our normal vector n, which is like the same thing, except it's with respect to this tangent vector. So our normal vector is the derivative of the tangent vector divided by the magnitude of that vector. Alright, so let's get into it. So I'm going to go back here to where we have our helical curve. And the first thing I want to do is I want to make the curve a function. So I'm going to make this function curve, and I'm going to feed it t, r, and mz, just some of the properties. We'll bring this inside of our function. Then I want to create an array, call it xyz. And to make the array, I'll do numpy.array and feed it x, y, and z values. And then we're going to return the array we just made. So we'll run that. Okay, looks good. Add some code here in the middle to take a look at creating our tangent and normal vectors, or calculating our tangent and normal vectors. So I'll call this, we're going to be using the Jacobian to do this, so I'll call this Jac tan. And the first thing we want to do is do the Jac.Jacobian of our curve. And now I'm going to create our function that is actually going to give us the tangent vector at a specified point. So I'll call that tangent. And tangent is going to take in t, r, and mz. So then we want to create our vector. So we'll call it vector v, and it's going to equal Jac tangent at the values we give for t, r, and mz. And as I said, the Frenice definition that we're going to be using is the vector divided by the magnitude of the vector. And we want to find the magnitude, which can be done with numpy as well. So we'll do jnp alg dot norm of the vector we just made. So now we have the vector and its magnitude, and to create our tangent vector, or I'll just call it the tangent vector t. We just do the vector divided by the magnitude. want to return t. So now we've made a function that we can call upon to get our tangent vector at a specified point along our curve, our curve. And I want to do the same thing for the normal vector. Actually, first I'll create kind of like the same thing we did for the tangent Jacobian, but this time, like I said, we're going to be taking the derivative of the tangent vector instead of our curve function. So Jacobian of our tangent. Now we'll define the function norm to take in t, r, and mz. Again, create a vector v. This one is the normal at the point we feed. I want to find the magnitude, which we can do the same way. J and P dot lane alg dot norm of the vector v. And this is our normal vector n. If we do the same thing, the vector divided by its magnitude. Since our variables that we created are just local variables, we can use the same thing, just vector and magnitude to keep it easy. Except in this one we want to return n, obviously. Shift enter. Alright, so it runs, no problem. And I guess now we can create a function that has both of these functions inside of it, and I'll call this the Frene-Serre function that will take in our curve function find both the tangent and the normal vectors, and then the binormal vector, which is just the cross product of the two that we've created. This one we want to return both of the functions inside of it. So we'll return tangent and norm. Looking good. So now, if I want to show kind of what this is doing, or at least check to make sure that it works, I can do tangent, comma, normal, and call upon the function I just made with t, r, and z. Or sorry, with Frene-Serre takes in a function, so I call upon it with my curve, and then I can check these variables I made at t, or at a specific t, r, and mz. So the first one I guess I'll do at a t of 0, which will just be the first, let's see. Alright, so it looks like this error had to do a little troubleshooting. Can be a little finicky, so you got to put in 0 point to specify that you're using like a float, not an integer. So this is the tangent vector at our t of 0 for the curve that we defined. So t of 0 would be the first point of the curve. Let me see if I can do this to show well. Zoom out a little bit. Alright. So our first point is right here, and the tangent vector should kind of follow the path of the curve along the outside, so it should come this way. And if we look at our tangent vector, it shows 0, 1, and then 0.13. So that's just the direction of the vector. So it is going 0 in the x direction, which is true. It should be going straight this way, and 1 in the y direction, which is also true. And then it just goes up a little bit following the path of the helix in the z direction. So that looks good. I can check the normal vector that we created at the same point. And that looks like it's -1, 0, 0. So if we go back to here, take a look at the first point again, the normal vector should point straight in towards the center of the helix. So as our normal vector shows, it goes -1 in the x direction, and then 0 in the y, and 0 in the z. So we're going, if we point towards the center of the helix, we are going -1 in the x, as well as 0 in the y and 0 in the z. So again, that also looks good. So for any point along the helical curve, basically what we can do here is just change our t value. So I could make it, like, just for example, 2, and we'll get the normal vector at a point of t with a t value of 2. So that would be just further along the curve, and it had no issues, so it should be good. Basically with this normal vector, something of note, this third value, since it's always going to be going like straight in towards the center of the curve, the z value should always be 0, because it's not going to be going up or down, it's just going to be going straight in. So it's good to see that that works. And then we can do the same thing with our tangent. We can look at it at any point along this curve, and it shouldn't have any issues, which is good. The z value is still this 0.13 as our curve's going upwards at a steady rate, so that's good. And we now have this function that defines our tangent and normal vectors of our curve, and as we look at the Fresnel's area, the binormal vector b that we'll be using in the future is just the cross product of these two vectors that we have now. So it looks good.